Okay, this is the scope section where we can define all the acquisition parameters. For instance, here on the right, in the scope setting, we can define the bandwidth, the spectral lines, and resolution, acquisition time, and so on. About the bandwidth, so the frequency range of our acquisition. If I put 160 Hz, that is a good data for our analysis, and then spectral lines. If I increase my spectral line, of course the resolution decreases, so for 512 spectral lines we have a resolution, so a delta f of 0.30 Hertz. And of course the acquisition time, that is the inverse of the resolution, is 3.2 seconds. Okay, here in the source control, we can define the parameter for our shaker. Output 1 that is enabled is our shaker. Here in signal type, if I click, I can choose the signal type that I want to use for running my shaker. So we can choose random, burst random, sine, burst sine, and periodic chirp. If I click on random, and here I define the level of my random profile, so 1 volt is okay. That is the maximum level that the random can reach us. In more, we have other settings, so the type of the signal, so white noise here or pink noise, the frequency definition, relative or absolute, depending on how you can want to take into account the acquisition bandwidth. Relative from 1% to 100% is okay. Start and stop times, other settings. The build up time is the time in which the signal reach the full level, so build up 0.1 second, and build down, sorry, is the time to decay, 0.2 second. If I click close, and now I go to start source, my shaker now is running, and you can see, if I click engineering unit to just to see G, the G unit, and then free. Okay. Here in the overview panel, there are several displays where you can see what's going on in your input. So we have these two that are, I don't know if you can see the point 1. So this is our impedance head. This is the input force, so in Newton, and this is the acceleration in G, and these are all the other accelerometers. Here in the detail panel you can see all the input, all the channel in detail. So if I scroll, okay, and of course this is a continuous random, a standard random. If I click stop source, we can see other signal type, so we can try to with the burst random. As you know, the burst random is a random signal which drops to 0 level after a certain time, and I mean it's a very good signal type for this kind of analysis, because you can avoid the leakage in your signal without the use of any windows. So I mean, it is the signal type that we will use for our experimental modal analysis. So 1 volt is okay for the level. And if I go on more details, we have the same parameter as before, but in this time we have also the burst definition here. So the burst time, here we can put 60%. That it means that we have 60% of random signal and therefore 40% of zero level signal. Okay, if I close here and I click on start, my shaker now is running, and as you can see we have our random signal. Okay, if we have our random signal here for more or less the 60% of the entire signal, 3.2 as I defined here, and then zero level. Now I click on stop. Okay, and I want to show you the remaining signal type. So if I click on sine and more detail, sine definition, the frequency, so I want a sine in 50 Hertz. Okay, close, start. Here we go, our sine here. Okay, if I click frequency, maybe yes, you can see our sine at 50 Hertz. Okay, so stop. Just to show you the last cyclic signal, that is the periodic chirp. Okay, the periodic chirp is, I mean, a sweep sine, a very fast sweep sine. So if I go on more, you can define the sweep definition. So sweep direction, you can choose up or down. If you choose up, your sweep go from low frequency to high frequency. The sweep time can be linear or logarithmic. Sweep time is the same of the burst random, so here you have to define the percentage of signal that you want. 60% is okay. So if I stir, okay, this is a typical periodic chirp signal. Okay, it's a very fast sweep sine, and then stop. Now I come back to the burst random, that is the signal type that we will use for the entire analysis. Level 1 volt is okay, so just have a look of okay, 60% of okay. So with the scope section we have done, so we can move to setup section. Okay, this is the test setup worksheet. Here in this section we can we can define which data we want to save and measure during the analysis. Here on the top, for instance, time, we can choose to save and measure the time recording, or if we want the auto power, we have to click on save. We can choose the amplitude scaling of our auto power, so RMS is okay, or the spectrum format, power, linear and PSD. And the most important thing that we need to remember it is to save and measure the FRF, of course. We can also measure and save the coherence or the dynamic stiffness. Another important stuff is the estimation method. We have the H1, HV or H2. H1 is okay for us, and also to define the reference. In our case, of course, if you remember, we have the input force in channel 1, so this is our reference, so input 1, and it's okay. And then if you go here on the right, and click on use scope setting, we have the same parameter that we have set during the scope. So the bandwidth is 160 Hz, the spectral line, and resolution of 0.30 Hz, and so on. Another important element is the averaging parameters here. Here you have to define the number of the averages. As you know, the more average that you take into account, and clearer is your result, and therefore you can, reduce the noise in your measurement and so on. So here we can put 10 averages. It means that if I remember well, we have a 3.2 second of signal, so in total 3 times 10, more or less 30 seconds of measurement acquisition. And then the conditioning, okay, here we have to choose the window about the reference and the responses, but we can put uniform windows for our signal conditioning, because we have chosen the burst random signal, and as you know, due to the form of our signal, doesn't need any window. So here everything is done, so we can skip on the measure section. And we are in the measure section. So here in this worksheet we can perform the first run. So here on the right, on run name, we can write burst random, and then 2, 3, 4, and 5 that are the measuring point for this run. Then we can activate the throughput recording here and click start. Now the shaker is running, and here you can see how many average have already done, and here how many left. In the display you can see, you can compare the average auto power, the average FRF, the average time, and so on. This is the instantaneous FRF, this is the average FRF, and you can change. Our input is the force input, and here you have all the other accelerometers, so 1, 2, 3x, 4y, and so on. So the run is done, so we can move on the navigator. And here we have the first run, so burst random 2, 3, 4, 5. If I open the run, we have all the saved data, so FRF, reference auto powers, response auto power, and so on. Here the throughput data, so if I want to plot them, okay, you just switch in real format. Here limits free. Okay, these are our recordings, so our signal. As you can see, we have 10 averages for a 32 second of total time, and of course our acquisition time was 3.2 seconds. As you can see, this is the typical format of a burst random signal, that it drops to zero level. Instead, if we go to the FRF here, we have our reference, the 0.1 Z, that is the input force. I click on both plot and okay, just to log scale. Okay, here our FRF. So we can see these peaks that probably are some resonances, so probably some mode of our structure. And of course now we have done the first run, but if you remember, we have to perform other 6 runs in order to cover all the other 22 points. Anyway, I don't want to show you all the run, but keep in mind that now I have to move and change the accelerometer in other 4 points, and therefore I have to go here in the channel setup and change, of course, the point name in 6, 7, 8, and so on. But probably I have to change also the direction, because when you are moving your accelerometers in other position, you probably are changing the local coordinate system of the accelerometer, and so you probably are changing that direction. Okay, now that I've already done all the 6 run, you can see here all the data. So we have the FRF for all the points, so the number 8, the number 9, moreover the 20, the 21, and so on. So we are ready for post-processing our data in order to perform our modal analysis and to obtain all the modal parameters. To do that, we have to add in tools. So we go on tools, add-ins, and we go on modal analysis. And in order to insert the LSE tools, and also in Polymath modal analysis, in order to add in the Polymath tools. So we click on OK, and you can just a few seconds. Okay. Here in the bottom, as you can see in the flow chart, we have other more sections. We have the time end off, that is the LSE tools, or we have also the Polymath and other section that we will see in the following. So we are ready for perform the analysis. The first step is to go on modal data selection here. Okay, if I click on refresh function table here on the left, as you can see here, there is the first column of our FRF matrix that we have obtained by using just one reference, the point 1, that is our input shaker, and we have 64 responses that go from the point 1 to point 22. Okay. Now, if I selected all my FRF and I selected the FRFs, you can see all of them here. I can add also the FRF sum. So if I delete the selected FRF, this is the FRF sum. As you can see, there are these peaks here at the beginning that probably are the rigid mode of our structure due to the suspensions that we are used for suspending our structure. And then there is a plateau here about more or less 20 Earth. And then this is the first peak that probably is the first mode of our structure. So here, if you add if you add nodes, marker, and names, here this is our geometry. So if I selected all the FRF, you can see all together here. Okay, then I go here in the FRF set for creating my new set of FRF. I can call my FRF set 2020 and I click on create. Okay, now I've done my my new FRF set and I'm ready to perform the modal analysis. As you know, there are two tools for performing the analysis. The time MDOF, that is the LSC tools or Polymath. You already know exactly the differences between these two tools, so I don't spend time to tell you the disadvantages and the advantages of them. And so we can start with the Polymath tool, because, as you know, is clearer and easier to handle for perform the analysis, and we can start with it. Now we are in the Polymath section here. As you can see, Polymath is divided into other three subsections: the bend, the stabilization, and the shapes. So three steps that you have to do for performing the modal analysis. As you can see here in the left, we have our FRF set. So if I select all the FRF and I click on selected function, all of them are displayed here. And or if you want the FRF sum, that's it. So in this subsection, we just to select the frequency band, so the frequency range in which we want to perform the analysis. In this case, I put maybe 40 here and 80. Okay, so it means that I want to skip these peaks that are the rigid body modes, and I want to perform the analysis just in 1, 2, 3, 4, 5, these 5 peaks here. Okay, let's move on stabilization. This is the stabilization subsection, and this is the stabilization diagram that Probably you have already seen it, and Professor Muki already explained all about it. But anyway, here we have to choose the stable poles for computing the mode shape. And as you can see, there are several markers, several letters here. The S stand for stable points, and there are also other letters. For instance, the V that stand for vector. That means that just the vector modal modes is stable, or the O that means that just the pole is stable. And probably you can find also the F for the frequency, or the D for the damping, depending on which parameter is stable. Anyway, we have to select just the stable point, so the S1. Here I didn't say that this is the modal size, so 30 is the default set here. Okay, so we select all the stable poles along the peaks here. So here, okay, we have selected just 1, 2, 3, 4, 5 poles, stable poles, and we have mode 1, mode 2, mode 3, mode 5, 4, and 5 with the corresponding frequency and the corresponding damping ratio. Then we can skip on the shape, the third subsection. And here we have in the poles panel here on the left our selected poles. So we can define the residue type for computing the analysis, so complex or real. I select real in order to have the normal modes. I have to write the processing name, so I can write real Polymath. Okay, and if I click on calculate, then I have the calculated modes right here. So if I drag the first mode here, and I have to animate my selection, you can see the mode shape of the first mode. As you can see, is a local mode of the roll bar. Okay, it is the bending mode of the roll bar. So our mode 2 is instead a torsional mode of our chassis, as you can see. Mode 3 instead is a bending mode of the chassis. Very nice. And mode 4, in this case mode 4 is just a local mode here of the back of our chassis. As you can see in the photo, the chassis in the back is not closed, and for this reason we have this local mode. Instead, the mode 5, okay, the mode 5 maybe is the more complex one, but is still a bending mode that involves, I mean, more the backside of our chassis. With Polymath, we have done everything, so we have estimated the 5 modes with the frequency, their damping, and the mode shape. Therefore, we can do the same analysis now by using the LSC tools. So we go here in time end off, and we are in the LSC estimation method section. So as you can see, this section has the same layout, Polymath. So we have here our three subsections, so the three steps that we have to do, the bend, the stabilization, and the shapes. Now we are in the first step, in the bend. As you can see here, we get our FRF set with our 64 responses. So if I select all my FRF and I click on selected function, maybe I put low scale here, okay. These are our FRF set. If I click on sum, this is our FRF sum, and as I said before, for Polymath in this section, we have just to select the bandwidth, so the frequency range in which we want to perform the analysis. So we move cursors. We perform the same analysis, so 40 and 80, okay, because we want to skip this bandwidth for the rigid body modes, and we want to calculate these 5 peaks, 1, 2, 3, 4, 5, okay. Then move on stabilization diagram. This is the stabilization diagram of the LSE tools. As you know, the diagram for this estimation method is more complicated. As you can see, there are a lot of computational balls here, and LSE give you a more complicated diagram. So you have to be careful to select just the stable pole. For instance, here you can take that one and probably that one. Okay, so now we have our 5 mode here, and we can skip on shapes. Okay, is the same layout. So here in poles we have the selected poles, so we can choose on complex or real. We take real in order to have the normal modes, and we can call real. Okay, now in the modes panel here we have our processing, real LSE. If we drag, we animate. Okay, if you remember, this is the first mode, the bending mode of the roll bar, and then our torsional mode, then the first bending mode, okay, our local mode in the back of the chassis, and the last one, okay. Okay, we have done the analysis also with the LSE tools estimation method. Now we can compare the two analyses, and we can validate our result by using these other two sections, modal synthesis and modal validation, yes, to validate our result. So let's move on modal synthesis. In this worksheet, you can synthesize the FRF set starting from the selected modes. So here in our processing we have real LSE, the last process that we have done. Here in modes, our modes, our 5 modes. So if you selected all the FRF set and you click on calculate here, just a second, and okay, we are now. By comparing these I mean synthesize FRF, that is the green line here, with the original one, with the measured one, that is the red one. You can check the correctness of the estimation of the select modes here. One thing that is the influence of the modes outside of the selected band, that in our case is from 40 to 80 Hertz, can be compensated with the upper and lower residuals here that we have taken into account during the calculation of the synthesized FRF. When you look the synthesized FRF, you will notice that the influence of the modes on frequencies above the selected band is approximated by a constant term here, that is our upper residual, that is the stiffness line. Instead, the influence of the mode on frequency below the selected band is approximated by another constant term, that is the mass line, that is represented by our lower residual. Okay. Other two important data that you have to check in this section are the correlation here. So if I go, okay, the correlation, more or less 100% of correlation is a very good result, and the error, that is the mean square error between the synthesized and the measured FRF. So if you, I mean, you can here display 6 plots simultaneously. You can, if you want, select the FRF, and you can scroll down just to check our FRF and to check the correlation and the error that you have. Okay. So now we can move on on the modal validation section. This is the last section of our analysis. In this worksheet, we can, as already say, validate our result by using the AutoMac button here and the complexity button, and we can compare our two analyses, the Polymath one and the LSCE, by using the Mac. So let's start with the AutoMac. We can start with the real Polymath, our analysis in Polymath. As you can see in the modes panel here, we have our modes. Okay, this is our mode. If I click on AutoMac and I go here on maybe it's matrix geometry. Okay, this is the Mac matrix. If I go on top, okay. As you know, the Mac express the degree of confidence between two complex vectors. In our case, this is an AutoMac, so our vectors are the same. And if the value of the Mac will be near to 1, it means that there is a linear relationship between the two vectors. Instead, if they are linearly, I mean, independent, the Mac value will be small, near to 0. As you can see, in our case, we have 100% along the diagonal and near to 0 on the off-diagonal elements, so a good result for our AutoMac. And then we can also calculate the complexity here. To show the complexity, maybe is better table. Okay. On the complexity, we have the MPC and the MPD. The MPC, as you well know, is the modal phase collinearity index that expresses the linear functional relationship between the real and the imaginary part of our mode shape vector, and this index should be I, near to 100% for real normal modes, and of course a low MPC index indicates probably a complex mode that could be due to, I don't know, error in the data measurement or mistakes during the analysis procedure. Instead, the MPD that you can see here is the mean phase deviation. This index is, the statistical variance of our phase angle of each mode with respect to their mean value, and in this case the MPD value should be low, so near to 0 for real normal modes, and as you can see we have 100% for all the modes in the MPC and 0% for and 0 degree for the MPD. That it seems to be too perfect to be real. Anyway, it means that we have done a very good analysis. Now we can compare the real Polymath, our analysis in Polymath, with the analysis performed with the LSE by using the MAC. So this is the MAC between the two processes. If I go on matrix geometry, once again view on top. Okay, as I said before, we want high value along the diagonal, so we have more or less the 100% here in the diagonal. If I click here, you can see, you can visually compare the two modes. In particular, this one is, as you can see, mode 1 in real Polymath, for real Polymath, so our analysis in Polymath, and this one is the one in the LSE process. You can compare all of them, so as you can see are very close from each other. And that's all. I already see everything about this first experimental modal analysis, so let's see you in the next video for the next experimental modal analysis on the car rim.